In this project, we built a virtual reality escape room developed by Babylon.js. This game is developed for Oculus Quest and features a variety of navigation, selection, and manipulation techniques. Instead of adopting existing interaction techniques as they are, we modified, enhanced, and combined them to come up with new techniques that better suit the needs of our game, the hardware capabilities, and constraints of Oculus Quest. The project itself is an interesting game to play, and also a testbed for the implemented interaction techniques. Our motivation can be divided by 4 parts. The recent prosperity of VR hardware market stimulated the growth of software ecosystem, especially for VR game industry. For consumer VR, potential customers are looking for interesting virtual experience rather than a serious working tool. From VR content creator, the question is down to what types of games are most suitable and can fully utilize the 3D nature of VR. Well, around the same time, a special type of puzzle game called escape room was also gained popularity worldwide. In an escape room game, the players are locked in a room, usually designed with a certain theme, and the goal is to find clues, solve puzzles, and break out. The immersion of being part of a story and the unconstrained ways of solving puzzles makes the game so unique that it quickly becomes one of the most popular games for people of all ages. In our project, we design and build an escape room in VR because we find the idea of escape rooms and virtual reality to be a good fit for each other. Immersion and interactions featured in escape rooms can be preserved and even enhanced in a way that is not possible in real physical world. The interactive nature of escape rooms also make it a natural testbed of different spatial interaction techniques with more intuitive and interesting tasks to perform. Luckily, there has been extensive studies in the area of spatial interaction techniques for VR that we can draw our inspiration from. Navigation is one of the most fundamental tasks in an escape room. The simplest of locomotion is controller-based navigation and teleportation. Position tracking or head tracking is also a common locomotion technique, and it has been built in most modern VR systems. In our project, we use adapted version of working in place and dual point world manipulation for horizontal and vertical travel, respectively. Besides being able to move around, a VR experience should also allow the user to manipulate the object in the environment. The most intuitive way is the basic grabbing. To select an object at distance, raycasting is a common solution. The pointed object can be attached to the ray and be manipulated like transportation and rotation. In our project, we implemented simple grabbing, voodoo dolls, and Homer for inspection and manipulation tasks.
In the remainder of this video, we introduced the implementation of some of our interaction techniques in this project. Among the 3 navigation techniques, teleportation is too simple, so we will only introduce the implementation of the last 2. For walking in place, our initial attempt is to use a step-based approach which tries to define what kind of motion of the controllers constitute a step, and then move the player one step forward whenever such motion is detected. Our definition of one step is when both the left and right controllers exit a certain radius away from the HMD. This approach does work, while the radius can vary greatly among different players depending on the way they walk. Therefore, we switched to another approach based on the average velocity of the controllers in a short time window. If the average velocity is greater than the threshold, we consider the player to be walking and we translate the player forward. By tuning the length of the time window and the threshold, we were able to find a value that works for all the players we tested on. For dual-point world manipulation, a very simple approach is to parent the whole scene to a transform node and attach the transform node to the player's hand. However, this will not work in our scenario because Cannon Physics Engine does not allow object with simulated physics to have parent, so we have to go for a much harder way to actually move the player. What we did, in short, is when the player is climbing, we keep track of the movement of the controller between each frame, and apply the inverse movement to both the controller and the HMD, so that the original hand movement is cancelled, and the player's viewpoint will move in the opposite direction as if it is climbing.
We implemented 3 selection and manipulation techniques. The first one is a simple grabbing. The idea is whenever the player's controller mesh or hand mesh intersecting with a grabbable object and hold the squeeze button, both left hand and right hand are fine. We set the parent of this object to player's hand mesh and also sleep its physical imposter. The second technique is remote inspection, which is inspired from Voodoo-Dogs, and this works for both hands. When a player would like to inspect an object at a distance, recasting to that object and holding the trigger button will create an instance merge at the location of player hand. At the beginning, we didn't realize that an instance merge cannot have another instance, which caused a lot of troubles. After we figured out the reason, we decided to do this, only creating the instance merge when a player pointing to a source merge. Otherwise, if a player already selects an instance merge, the program will first find a source merge, then create another instance merge attached to the controller. If the inspected object is too small or too big, players can change the size of the object by grabbing the trigger button on the other hand, and change the distance between two hands. The size of the inspected object will automatically modify its size based on the length of a manual line between the two hands. The third technique is remote manipulation, which is inspired from a technique called Homer. This method allows players to grab an object at a distance. The behavior of the target object is the same as the player's hand teleport to the center of the target object. Therefore, both position and rotation changes of the player's hand will be applied to the center of the object. It also works for both hands. The biggest challenge to implement this approach is hard to deal with rotation. Position change is easy. We did it by recording player hand position of the last frame, then let the current frame hand position subtracted to get the change of a player hand position. Next, add this change to the target object center. Rotation seems like it can be done by the same procedure. However, this time we have to deal with the change of a rotation quaternion. After trying multiple times, we still cannot get the result as we wanted. So we decided to use a trick to implement it. If a players want to achieve remote manipulation, we will firstly create a transform node as the center of the target, then set the rotation quaternion of this transform node the same as the controller rotation quaternion in every frame. Then, set the target parent to be this transform node. After that, the player is able to manipulate this object remotely. Problem solved. Implementation of system control part is not that time-consuming as navigation and manipulation. We basically did 3 things. The first one is 3D tooltips. When the first time players enter our escape room, a didactic prompt user interface will show up and teach players how to do remote inspection and remote manipulation. We implement this by using text blocks and a dynamic texture wrapped in Babylon.js. After players finish all the tutorial, the text block will change its visibility to 0 slightly, until it disappears. This visual effect was completed by keyframe animation. For the 3D button as a numeric keyboard, we just use a feature that Babylon has already provided us, such as 3D button and a virtual keyboard.
Finally, I want to talk about collision handling in our project. We're using the Cannon Physics Engine in our project, which takes care of 90% of the collision, while there are some other important places where special treatment is needed for collisions to work properly. One such example is camera collision. We find that the collision of XR camera cannot be handled by the engine directly, while some indirect approaches are available. For example, applying the physics to an invisible object and manually binding the transformations of the XR camera to this object. We find them to be not very elegant and may lead to performance issues. So instead, we use a simple hack which defines which areas in our scene correspond to obstacles and cannot be entered. Whenever the player is using continuous locomotion techniques such as walking in place or climbing, we test to see if their destination falls within these invalid areas and will stop them from moving if it is. Another collision issue is related to the shelves. If we're using simple box imposters to represent these shelves, we will not be able to place anything on them because technically these objects are inside its collision body. Using a mesh imposter is expensive, so we try to set up plane imposters for the contact surfaces of the shelf. However, with plane imposters, objects keep falling through the shelf because continuous collision detection is not enabled. In order to avoid the expensive continuous collision detection, we ended up building our own custom collision body, as is shown in the image down on the right.